Hello, everyone. Good morning, good afternoon. I don't know where you are. My name is Roberto Roland. I am a senior consultant at Geovariances, and I've been working in resource estimation for many years, supporting mining projects around the world. And today, I will be presenting week 3 of this webinar series, which is all about maximizing resource confidence. So in this session, I will show you how advanced geostatistics techniques, especially using Isatis.neo, can help you better understand uncertainty and support the decision-making process about your resources. So we'll go through not just the theoretical side, but also practical examples. So it means that by the end, you will see how these methods can directly support real projects or your specific projects. So let's get started. So in this presentation, we will begin with an overview of the traditional resources modeling workflow. From there, I'll highlight some of the key challenges it presents, particularly when it comes to calculating recoverable resources and assessing uncertainty. Next, we will introduce geostatistical conditional simulations and explore how they can be applied, especially in the resources classification and risk analysis. And finally, we will look at how these techniques can be put into practice using Isatis.neo, with practical examples to show their value in real-world projects. Well, so in every mining project, one of the first steps is to model the ore body based on the available data. In the traditional workflow, this starts with defining the ore body geometry, essentially delimiting the mineralized envelope. And this can be done through explicit modeling, implicit modeling, or often a combination of both. And once the geometry is established, the next step is to populate this envelope with ore grades. And typically, this is done by interpolating the grades into the SMU grid nodes within the ore body, most commonly using ordinary kriging. So if you've been following our webinar series, you may remember that last week, Hawking demonstrated this workflow in practice using a combination of Studio RM and Supervisor. So ordinary kriging provides the best estimate for a block. However, it has some limitations. When the drill hole spacing is larger than the block size, kriging tends to smooth the results way too much. So in practice, it means that the estimates will show much less variability than the actual data. In other words, the histogram of the estimates becomes overly concentrated around the mean. So we squish the variogram of the data around the mean. And usually after completing the estimation, especially during the exploration stage of a mineral deposit, one of our main goals is to calculate global tonnages. But when we rely on an overly smoothed model and derive a great tonnage curve from it, the results are biased. It means that tonnages at higher cutoffs are underestimated and tonnages at lower cutoff are overestimated. And this happens because of kriging inherent smoothing effect. So this is our first major issue. In exploration stage, when the drill hole spacing is wide compared to the SMU size, our tonnage calculations will inevitably be biased. On one hand, we are dealing with natural phenomena, which are inherently uncertainty. So geological heterogeneity, incomplete information, because we gather information from sparse drill holes, mean that uncertainty is unavoidable. And in the other hand, kriging provides a single best estimate, which is a deterministic result. And as the statistician George Box famously said, all models are wrong, but some are useful. And the key is to understand how wrong our models could be so we can make better informed decisions. And this brings us to the second issue. Unlike probabilistic techniques, kriging does not represent uncertainty. And it does not allow us to properly manage its consequences. So in summary, kriging works well during the production stage when data is dense and closely spaced. However, in the exploration stage, kriging cannot provide an unbiased estimation of the grade tonnage curve. In addition, because it is a deterministic method, it does not allow us to assess the inherent uncertainty in the resource modeling process. So to address this limitation, several nonlinear geostatistical techniques were developed, such as uniform conditioning, multiple indicator kriging, multi-Gaussian kriging, and conditional simulations. In this presentation, we will focus on conditional simulations because while the kriging-based nonlinear methods can be complex to implement and rely on very strong point-to-block distribution assumptions, conditional simulations requires only that the conditioning data follows a Gaussian distribution, and that's it. And it makes it a very powerful and more practical approach to handle the uncertainty. So the idea behind geostatistical conditional simulation algorithms is to generate multiple equiprobable realizations of the ore body. And these realizations honor both the data distribution and the spatial continuity described by the variogram. And because the variability of the data is reproduced, we avoid the smoothing effect, meaning the grade tonnage curve is no longer biased. And since we generate multiple equiprobable realizations, we can also quantify and assess the uncertainty. In other words, conditional simulations directly address the two key issues we discussed earlier. Different types of conditional simulations are available in Isatis.neo. The sequential Gaussian simulation, or SGS, is the simplest method to understand and implement, both mathematically and computationally. However, it is very slow. And for large projects, its application quickly becomes prohibitive. It's slow by design because it is conditional. The turning band simulation, TBS, is a spectral approach. In contrary to sequential indicator simulation, its mathematics and implementation are way more complex, but it has the advantage of being extremely fast. So unlike the sequential methods, TBS can be parallelized. So it makes it much more efficient, especially for very large data sets. And finally, the stochastic partial differential equations, or SPDE, is another powerful simulation method, and it has the added benefit of handling local varying anisotropy in a more elegant and flexible way than SGS. And turning bands cannot handle local varying anisotropy by design. So we mentioned that conditional simulations must honor both the data distribution and the spatial continuity represented by the variogram model. And to accept our simulations, we need to check that this reproduction is indeed correct. So first, we verify the variogram reproduction in the normal score space. Then we check the histogram reproduction in the raw unit space. And in addition, we assess the accuracy of the simulation, which tells us whether they are properly covering the uncertainty space. So for example, we expect about 10% of the simulated values to fall within plus or minus 10% of the true value, about 50% within plus or minus 50%, and so on. Once we have a set of validated simulations, the question becomes, what can we do with them beyond producing an unbiased calculation of recoverable resources as we saw it is possible? So the first application of simulations I'd like to discuss is mineral resources classification. Simulations provide several important advantages compared to traditional methods based on kriging variance or geometric rules. Conditional simulations generate multiple equiprobable realizations, which means we can assess the full distribution of possible outcomes instead of relying on a single deterministic variance, as in kriging. And this allows us to capture effects like heteroscedasticity or the proportional effect that kriging variance cannot capture. It means that high-grade zones usually shows graded variability, and simulations properly reflect this dependency on grade values. Another key advantage is that simulations enable us to use probabilistic criteria for the classification. And these criteria are usually easier to justify and communicate than purely geometric rules, which often do not show some statistical meaning. So it's much clearer to say that a measure block falls within the average grade, minus plus 50%, 95% of cases, than to say that a measure block was estimated using 8 drill holes within 100 meters, for example. The second simulation application I want to discuss is risk analysis. From a long-term perspective, simulations can feed directly into stochastic mining planning. So instead of relying on a single best estimate model, we use all the realizations generated through conditional simulation as inputs for planning. In this way, uncertainty is no longer hidden behind averages and averages and averages, and it becomes explicit part of the process. And using this approach allows us to generate probabilistic forecasts such as P10, P50, and P90 for tonnage, grade, metal recovery, or even cash flows. And this forecast provides a much clearer picture of both the upside potential and the downside risk rather than a single deterministic number generated by kriging. From a short-term perspective, simulations can also be used to assess the uncertainty of specific elements, such as the SMU, a dig line, even a stope in an underground mine. So when your boss asks how much money we are going to make with this dig line, for example, instead of giving a single exact number, which is likely wrong, you can provide the P10, P50, and P90, for example. And that is much more realistic and useful for a decision-making perspective. In 2015, Diogo Silva, as part of his thesis, he compiled data from more than 150 NEI 43-101 reports published between 2011 and 2012. And the results shows that 54% of the resources were estimated using ordinary kriging, 29 using inverse distance, and only 0.7% using conditional simulation. As expected, we see the same trends in resources classification. About 50% of the reports resources were classified using neighborhood restrictions, and around 25% were based on drill hole spacing. And Clayton Deutsch highlighted in his talk at the AUSA-IMM 2025 Mineral Resource Estimation Conference that kriging is cheating and conditional simulations should really be the standard for resource reporting. But the reality is that conditional simulations are still not widely adopted in the industry. And why is that? Well, first we need people capable of understanding and applying these methods. We also need specialized software with enough performance to handle the simulations. On top of that, many downstream users, like for example, the mining planning team, the operation, they are not yet prepared to work with probabilistic models. And of course, many companies' protocols still require reporting based on kriging. And beyond these technical and operational limitations, geostatistics may also be a victim of its own success. Kriging has worked well enough for many projects because deterministic methods have historically produced decent resource and reserves estimates, especially when data density is good. And kriging is so robust that it often works reasonably well, even if the parameters are not properly defined. In simulations, on the other hand, they are way more sensitive and more challenging to validate. But here's the key points. I would much rather be approximately right than precisely wrong. So maybe we should think about doing our best to start using simulations to estimate our resources, to classify our resources, and to report our resources. And with that in mind, let's move to our demo in Isatis.neo. The first thing we did was importing everything that Hawking created in Studio RM and Supervisor. So Isatis.neo allows you to import data from many different sources in many different formats. However, to import any information from a Datamine software is very, very easy and very, very seamlessly. So we just go on Home, Imports, Datamine, and we can import directly the Datamine files. So this is what we did. We imported the composites, and we imported the subblock estimated model and its parent block model. So here we can see the copper assays, the copper composites, have a bunch of drill holes. And we can also have a look at the estimates by ordinary kriging in the subblock for one of the shears. So we have different lithologies here, shear A, shear B, and an intrusion. And Hawking model the shear A because this is the mineralized ore body in this deposit. The next step is to get the variograms, the Gaussian anamorphoses, so we can do our simulations. In Isatis, under statistics, we have a complete EDA tool. So here we have many options for anything related to statistics. So we can model variograms, we can do our Gaussian anamorphoses, we can model the trends, we can plot any of the statistics tools like histogram, cross plots, box plots, SWOT plots, 8 scatter plots, variogram map to help us defining the principal directions of our variograms. However, Isatis is fully integrated with Supervisor. So instead of modeling the variogram myself inside Isatis, I'm going to use the variogram Hawking model last week. And as everything related to imports, we go under Home, Supervisor, and here is just a matter of informing where the supervisor project is and match together the correct variables. So if you are using the same names, it's even easier, but you can use different names in the different projects, and you just need to assign the correspondent variable name. As you do this, you can import it, and you will have the variograms that came from Supervisor. Well, now we have all of the tools we need for simulation. And since we want to produce our simulations in a very high resolution model, then we can upscale this resolution to any scale we want. For example, the SMUs, the stopes, dig lines, wireframes that represents 1 month of production, wireframes that represents a year of production. We want to create a fine grid, a very fine high resolution grid. So to do that, we took the parent grid. So the parent grid is 5 by 5 by 5. And we refine it to create our simulation grid, which is 2.5 by 2.5 by 1. Then in Isatis, under the menu Interpolation, Risk Analysis, we have the simulation task. So all the simulation algorithms are stored in the same task. When you click on it, a wizard will open. So you have to fill the first window, click next, fill the second window, click next, fill the third window, click next, and so on. So here we are informing the geostatistical set, which is the variogram together with the Gaussian anamorphoses. The geostatistical set are imported objects in Isatis since they are inputs for simulations and kriging and so on. We set that we are only doing our simulations inside the shear A or body. We inform the output file, which is the simulation grid, only inside the shear A. We want to do point simulations. We want to use turning bands simulation. In the next window, we define the search neighborhood we want to use. In the next window, we define how many realizations we want and what the output we want. So we want the Gaussian simulations and the simulations in the raw units after back transform. You have some options to calculate recoverable resources above cutoff and to calculate some uncertainty measurements as well during the simulation. As soon as you click run, Isatis will run and return the simulations. I'm not going to run it right now because it will take some time we don't have. So at the end, we will have a set of 100 simulations for the copper variable. Here you can see the realization number 1, realization number 2, realization number 3, and so on. Remember, we need to validate. If you don't validate your simulations, you are not doing simulations. So this is what we are doing now. We have to validate it. Under risk analysis, you have this option, simulation validation. It's a very easy tool to use. We just inform the input, the data, and we inform the output, which is the grid. And Isatis will calculate the histogram, the variogram, the SWOT plots. Again, I'm not going to apply it because it will take some time. But I already did it, and I have the results stored as chart files, which are plots that we can save to visualize it later, as we are doing now. So we can check the variogram reproduction. The variogram is well reproduced in the 3 principal directions. We can check the reproduction of the histogram. The histogram is well reproduced, and we can see the SWOT plots in the 3 principal directions, and we can see that simulations are indeed reproducing the data behavior. Still under risk analysis, we have the accuracy plot to check if our simulations are covering the whole uncertainty space. And here is the same thing. We inform the geostatistical set, we inform the moving neighborhood we use for simulations. And as soon as we click run, we have the results that will look something like this. So what we expect is a line plotting very close to the 45-degree line. And indeed, this is what happened. So we can accept this set of realizations and say, all right, these realizations are validated, they are checked, they reproduce the data statistics, and they are also covering the whole space of uncertainty that we needed to cover. So the next step is what to do with these 100 realizations. First thing, we can classify resources. To classify resources, usually we want to classify the resources in the SMU supports, because classifying in this point support is not useful because we mine using big equipment and not using a very small teaspoon. So we first upscale the simulations to the SMU supports. Assessing the uncertainty directly on the SMU support is usually not very efficient because as we mine SMUs, we do not process SMUs, we do not sell SMUs. So usually what we want to do is to consider the uncertainty that represents a bigger volume that is compatible to the quarter production, the monthly production, or something along this line. So what we did here is first upscaling to the SMU support. Then we can use a moving window to consider this production volume, and we can use the simulation post-processing tool in Isatis to calculate in the uncertainty tab the relative to mean estimation error. So it means that we are calculating the P95 minus the P5 divided by 2 times the average. And we have a map that looks like this. And we can use this variable to create our classification variable. So we are doing cutoffs on this maximum estimation error variable to generate our classification. So this is what we have at the end of the process. And we can see in green, measured resources, in yellow, indicated, and in orange, inferred. And it makes sense where we have a high concentration of drill holes, we are measured. Where we have some drill holes, we are indicated, and no drill holes inferred. And remember that simulations also takes into account the proportional effects. Finally, what we can do is to assess the risk. So in this case, we have different stopes planned for this ore body. And we have these stopes in order. So first stope, second stope, third stope, fourth stopes that's going to be mined along the life of the mine. And with some Python. So if you are familiar with matplotlib and NumPy, we can, with a very short 42-line code using a calculator, you can generate a risk analysis plot for your stopes that looks something like this. So here we are assessing the uncertainty in relation to the grades for the first 53 stopes for the first year. And we can see the P50, the P10, and P90 for the realizations inside this stope. So we upscale the point simulations to the stopes, and then we calculate P10, P90, and P50. And we can see that for some stopes, we have a lot of uncertainty that we might want to sample a little bit more, or we want to put a red flag and say, beware this stope because the uncertainty might be too high. So this is how we can use simulations to better understand our resources and help us in the decision-making process.